The objective for this video is to explain the difference between potassium wasting and potassium sparing diuretics. We are going to start by focusing on the collecting duct, specifically on the principal cell. The principal cell contains two important channels, the epithelial sodium channel, aka the ENaC channel, and a potassium channel. Both of these channels exhibit passive transportation of these ions based on an electrical gradient. This ionic gradient is created by a sodium-potassium pump that uses ATP to import 2 potassiums into the principal cell and export 3 sodiums into the blood. So before any sodium arrives to the collecting duct, the principal cell is full of potassium and lacking of sodium, and its charge is slightly more negative than the collecting duct. Thus, the principal cell is prepared for a sodium influx from the collecting duct. Now, what happens when sodium enters the principal cell? So let's remember some pre-med physics and chemistry principles. Sodium and potassium are both cations, i.e. they both exhibit a positive charge. As sodium enters the principal cell, the cell becomes more electropositive, which causes the potassium to leave. So in renal terms, as sodium is reabsorbed into the principal cells, potassium is secreted into the urine. Furthermore, the more sodium entering these cells, the more potassium secreted into the urine. This is the key concept in understanding potassium wasting versus potassium sparing diuretics. Everything else discussed in this video is based on that concept, so really make sure you get it before moving on. Okay, so now let's zoom back out and think, what determines how much sodium goes to the collecting duct? Here we have sodium traveling from the glomerulus through the tubule from left to right, with sodium being reabsorbed at each segment of the tubule. Interestingly enough, each segment of the tubule does not reabsorb the same amount of sodium. The proximal convoluted tubule reabsorbs the most, 65 to 80%, while the collecting duct reabsorbs the least, only 2 to 5% of the sodium. So let's say at the loop of Henle the sodium channel is blocked. Then more sodium will get to the collecting duct. As we discussed, this will lead to more potassium being secreted from the principal cells. When a diuretic causes more sodium to arrive at the collecting duct, then it is a potassium wasting diuretic, as more potassium is excreted out into the urine. Another way to think of the distinction is if the diuretic blocks sodium reabsorption in any part of the tubule other than the collecting duct, then it is a potassium wasting diuretic. So by that logic, if the diuretic blocks the ENaC channel in the collecting duct, then it's a potassium sparing diuretic. Here we have a potassium sparing diuretic. Once again, the key is the relationship between the ENaC and potassium channel. If the ENaC channel is blocked and less sodium enters the principal cells, then there will be less of an electrical force causing the potassium to be excreted into the urine. So really, you can think of potassium sparing diuretics as potassium retaining diuretics. Whether you want to understand the physiology or not, it's important to know the difference between potassium wasting and sparing diuretics because of their involvement with hyperkalemic and hypokalemic states. At the least, remember, there are a lot more wasters out there, but those sparers are absolutely principal.